In the previous video, we're able to establish the processes in solving Bernoulli's equation. We had an example in the previous video, so please review on that. But the point there is we can actually identify whether this equation is Bernoulli or not according to its standard form, and then later on use a specific step to transform this Bernoulli equation in standard form into an equivalent representative linear equation in order for us to solve for the intended variable y. The standard form is in this form: dy over dx is plus p of xy is equal to f of x y to the power of n, where n cannot be 0 nor 1. So let's try to see if this is really a Bernoulli equation. Since we have an x here, let's multiply all items y 1 over x, or all terms. So you have dy over dx plus 1 over xy plus, not plus, equal to 1 over x times 1 over y squared. Let me rewrite this in terms of y to the power of n. This is dy over dx plus 1 over xy is equal to 1 over x times y to the power of negative 2. This case, our n is negative 2, and this fits the idea of a Bernoulli equation. Together with that, we can get here a value of p of x being 1 over x, and you have your f of x here also 1 over x. But again, this cannot be solved by the linear equation first, because we need to transform this into an equivalent linear equation following this step. We're going to remove this certain items so that this would become linear, because the idea of linear is that the right hand side should only contain all variables of x, in short, f of x only. So we can do that by multiplying. Let me copy that here. Okay, plus 1 over xy, 1 over x y to the power of negative. We are going to multiply y squared to neutralize this, but let's also do the same thing on the other, y squared. Hence, you will have the form y squared dy over dx. Okay, you will have here plus, you will have 1 over x y cubed. Okay, that's y cubed, right? Is equal to 1 over x now. This is not yet in linear form because we have this. Our goal is, now that we are done with this, our goal is for this to only have a power of 1. But since it's y cubed, how can we do that? The goal here is to let another variable, let's say z, equal to y cubed. Okay? So that this will be transformed into an expression 1 over x. 1 over x and now z instead of y cubed. But since we have this expression as well here, this expression here, let's try to, sorry for this, yeah. So let's also try to get its equivalent d of z, because we need to also change or remove d of y. This is actually 3y squared dy, right? So what is dy? Okay? Or what is y? Y dy. So y dy here is, if you're going to divide both sides by, let me remove this first, by 3, you will get here 1/3 of dz is equal to y squared dy. Okay? So 1/3. This would mean transforming this entirely into an expression instead of y will have z. You will have here, this is also 1 over x. This is now 1 over x times z. Your y squared dy, this one here, will become this value 1/3 of dz over, you will have 1/3 dz over dx. Hopefully you got 1/3, because we would like to have dy of y squared over y squared dy, which is this expression. Now, the standard form of a linear equation, this is not a linear equation, is that this is only 1. So let's multiply 3 on all items. Therefore, we get this dz over dx plus 3 over x z is equal to 3 over x. And yes, this is already a linear equation where your p of x let's have p sub 1 of x to differentiate with the p of x given here is equal to this form, 3 over x. And your f1 of x is also this form here, 3 of x. Okay? So this time, instead of y, let's solve for z. Later, once we are done with z, we'll return to this equivalence to solve for y. Okay? So let's proceed here. To use p sub 1 of x, you will get your integrating factor, which is e to the power of p sub 1 of x dx. So e to the power of the integral 3 over x dx. We can have here e times raised to 3. We have here 1 over x dx. E to the power of 3, that's natural logarithm of x. Okay? Using the power law, you will have here e to the power of logarithm of x cubed. Hence, the integrating factor mu of x is equal to x cubed. Okay? That's the process of getting the integrating factor. You just need to review as well some of our videos on our channel because we're already discussing that as well. So with this, we can solve for z using this expression, mu of x, z instead of y, is equal to the integral of mu of x, f sub 1 of x, not the other one, but this here, dx. Okay, let's continue. So this is x cubed. Okay, that's x cubed. The next form will be z equal to, you have here x cubed, f sub 1 of x is 3 over x dx. Right? So this would be simplified. You have x cubed, z is equal to 3x squared, 3x squared dx. Okay? So x cubed, z is equal to, call this one. We'll have factor 3 x squared dx. So x cubed z is equal to 3 times, you will have 2 x cubed over 3, if I'm correct. Then you have here plus c. You can cancel that. So x cubed z is equal to x cubed plus c. Okay? Now we're solving for z. You would like to solve for z, so let's divide or multiply all parts here by 1 over x cubed. 1 over x cubed. So we have z is equal to, we have 1 plus c over x cubed. Right? C over x cubed. That's our z. Now take note, z earlier is represented by y cubed. Y cubed. So this can be written as y cubed is equal to 1 plus c over x cubed. Now this is already acceptable based on some references, but if you would really like to get y, then you will get the cube root of the expression 1 plus c over x cubed. Okay, so basically we are now done solving for our equation, Bernoulli equation. We now solved y using the solution for our z, and this is now the solution intended for our given item. So we were able to solve this by understanding the Bernoulli equation, and then later on understanding the equivalent linear equation out from it, so that we would be able to solve the specific item. Thank you very much for watching.